All right, welcome to Lecture 9 of GD50. Today's topic is Dreadhalls. So last week we ventured into Unity, our first foray into 3D, and not only 3D, but also just getting our heads and hands around the Unity game engine, which is, among Unreal and others, sort of the most popular game engines in use for 2D and 3D games. And last week we did sort of a 2.5D style helicopter game whereby everything was in 3D, but we were still aligning things based on just two axes, the X and the Y, I believe, possibly the Z and the Y, I don't remember, but two axes versus three axes. Today we'll actually be diving into using all three axes available to us in Unity 3D in the context of a game called Dreadhalls. And so what Dreadhalls is it was a VR game, actually the first VR game that I ever played on the Oculus, the Gear VR, Samsung Gear VR, and it pits you in sort of this dark and eerie 3D maze where you don't really know what's going on, and you can go around and get collectibles and encounter creatures and stuff, as you can see in the bottom right screenshot there. Today's example is going to be a little simpler, but it allows us to explore things like procedural maze generation and first-person camera controls. So last week, recall, we were using sort of a third-person camera, whereby we were sort of far back on the scene. Today, we'll actually be using a first-person camera, where the camera is effectively our eyes, as if we were walking around in the maze ourselves. Unfortunately, we won't be using a VR demonstration this week, but next week I hope to put together sort of a VR sampling using this project so we can see how this works in VR and how Unity's toolkit works in VR. So some of the topics we'll be covering today. We'll be talking about texturing. So recall last week, the helicopter and all of the items in our game were just sort of flat colors. They didn't really have any textures associated with them. We'll talk about how to assign textures to materials and how to apply those materials to objects in our scene. We'll talk about materials and lighting, so not only materials, but also the different kinds of lights that Unity supports, and a few details about those. We'll talk about, again, 3D maze generation, so we'll have a simple but effective algorithm for creating a 3D data structure to represent our level, as opposed to previously where we had just a tile map that we could generate to give us the appearance of walking around in some sort of 2D world. Now we'll actually perform a similar operation on data, a 2D array, but we'll take that array and we'll actually create 3D blocks and create a maze that we can walk through in 3D space, which is kind of fun and interesting. Last week we only had one scene in our game, which was just a play scene, and even though we had sort of like a game over state within that scene, we didn't transition between scenes, we just sort of reloaded the same scene. Today we'll have a title screen and a play scene, which sort of is an evolution of the idea that we had in Love 2D, where we had a state machine that was governing our entire game in terms of the different states that we could be in, whether it was the title, the game over, the play state, and so forth. Unity does the same thing with scene objects, which are effectively a snapshot of a series of game objects aligned in a particular way in the editor. We'll talk about fog and also global lighting and certain other things that allow us to create an atmosphere conducive to the sort of feel that we want to get in our game today, which is sort of creepy and eerie. And lastly, when we talk about how to create UI elements in the game, we'll talk about Unity 2D, its canvas object, and text labels and some other things, and how those all operate, which is sort of two sides of the same coin. Unity 3D also comes bundled with Unity 2D, a set of tools used to make not only 2D games, but also 2D interfaces that you can apply to your 3D games. So first, a demo. Now, I've been sick for the last week, so I'm not going to ask for anybody to come up and demo just because I don't want to get anybody else sick. So I'm going to just go ahead and show just this lecture, the game that I put together for you. So here I have two scenes. Notice here I have a title scene and a play scene. I'm in the Unity editor right now. I'm going to load up the title scene here, which I've done, and then notice that it has sort of a game view and a scene view. I'm going to hit play. I'm going to make sure that it's set to maximize, which it is. And so we have sound here, so we should hear audio. I'm going to hit play. And notice that we have sort of like this ambient, creepy music track playing. We have we could have easily done this in Love 2D. This is just black screen with two text labels on it. And this is done with Unity's 2D UI toolkit. And so it tells us to press enter. So if I press enter, we instantly get teleported into kind of like this maze, this creepy looking maze. And so I can walk around in this maze And there are a few things going on. So can anybody tell me some of the things they notice about the scene? What jumps out at them? What are some of the elements, if you were to put this together yourself, where would you start? What are the pieces that we can put together here? Yes. Yep, there has to be a ground that you can stand on, and there is. So we're generating not only walls in our scene, of course, but we need a ground to sit on. And also, if you look up top, it's kind of difficult to tell, but we also have a ceiling. So ground and a ceiling and walls. Some kind of lighting, yes. And so in this case, we're actually using ambient world lighting as opposed to having a light source. So we'll take a look at that. In last week's lecture, we used, or 2 weeks prior's lecture, we used a directional light object. But in this case, we have no lights in the scene. We're actually using Unity's world lighting, which we'll take a look at soon. When we walk around, notice that I can move where my camera's looking with my mouse. So we're actually controlling the camera with a first-person controller, an FPS controller, which is actually a component that Unity provides to you. And then notice, eventually, if we keep exploring the maze, we come across this little thing here, which is a sort of a pickup. And when we pick this up, we get sort of like this piano, weird, creepy piano sound, and then the scene reloads. Does anybody notice anything about what we see in the distance, like how that's affected? Like if I'm looking at this wall right here, for example, it's kind of hard to tell, but as opposed to like down this hallway, what's the difference there?
The light source is further away, I guess?
The light source is further away, kind of. So what we're experiencing here, what we're seeing is it's a graphics sort of concept called fog. And so what fog lets you do is it effectively adds color to the scene based upon how far away the objects are in the scene. It multiplies color onto them, and it gives you the illusion of looking as if you're surrounded by fog, basically. And it's been around for a very long time, back even as far as the N64 days, and we'll talk about that later today. And it's actually incredibly easy to add that into a game with Unity and its world lighting system. Any idea as to how fog, not only in terms of aesthetics, but how it could maybe help with performance? Yeah.
You don't need as much pixel clarity because it's already blurry.
You don't need as much pixel clarity. Kind of. The big thing about fog and the way that it was used a long time ago is that because eventually things are completely opaque beyond a certain point, you don't need far draw distance in your game. So you can actually, like, dynamically, you can omit rendering things that are a certain distance away because you wouldn't be able to see them anyway. And so this was an optimization technique used a lot back when draw distance was a huge bottleneck on computers and video game consoles back in like the 90s, for example. Like Silent Hill, the game for PS1, was almost exclusively fog, and you could see very little in front of you, and we'll see a screenshot of that later. And they use that to boost their performance and also to provide a certain aesthetic. And then one other thing you might be paying attention to is there's a sound on loop, just sort of this creepy sort of whispering sound, and that's to just add atmosphere, right? Just because without it, we would, it's little things like that, especially in horror games like this. The atmosphere can be everything. So with very simple ideas, fog, some whispers, first-person controller, sort of tight hallways, you can produce something that's pretty scary. Now, there are a few things missing from this. Namely, there's nothing that's going to come at you and attack you. But it would be not terribly difficult to add, but because we're using procedural generation, you would need what's called a nav mesh, and you would need to generate that procedurally so that things could follow you in 3D space. We might have some time to talk about how to do that a little bit later today, but that's not implemented in this particular lecture. But it would be not too infeasible to accomplish. But those are some of the pieces that we'll take a look at today. This is the title scene. Notice that there's not a whole lot here, actually. So if I zoom back out, we can see, canvases are huge in Unity, just because it's more optimized for the engine to render them that way. But we can see, even though it's a 2D sort of UI, it's very visible in 3D space. And if we click this button here, we end up getting, oh no, that just brings us into, sorry, click this button here. That brings us into sort of the 2D, Unity 2D mode. So now we're interacting with things in 2D, and I can actually click on this label and move it around in 2D as if we were using a 2D game engine as opposed to a 3D game engine. So we'll look at that a little bit later. This is just the title scene. So the play scene itself, I'm not going to save that. The play scene itself, I'm going to go from 2D back to 3D here, is pretty much empty. So we have a first-person controller here. This is the FPS controller object. Does anybody tell what basically constitutes an FPS controller just by looking at the scene here? What are some of the pieces that jump out at you?
I thought you just put the camera right where the player is, or right in front of the player.
Exactly. You put the camera right where the player is, effectively where their head should be relative to where their body is. And their body, what's constituting their body here? Can you tell?
It could just be a cube. It looks like a cube in the middle there.
It's actually this capsule right here. I don't know if you can see it. There's this capsule here, this green capsule. It's a little bit more organic feeling than a cube necessarily, but you could use a cube as well. But a capsule is how character controllers in Unity are represented. And character controllers sort of come for free in Unity, which is really nice. They're part of the standard assets. So if you go to import package in Unity, if you're going to assets, import package, there's a lot of packages that come for free that sort of bootstrap you. Notice there's like 2D packages, cameras, characters. The characters package has 3D characters, or third-person characters, first-person characters, some that are physics-based, some that are not physics-based. This particular controller is not physics-based, meaning that we don't apply forces to it. We move it around. It's kinematic. It is affected by gravity, so in a sense it kind of is physics-based, but it's not strictly physics-based like a rigid body and a rigid body would. And the collisions that occur between this and another rigid body aren't the same as they would be if we were to make this a purely rigid body-based character controller. There is a purely rigid body-based character controller that you can import. I haven't experimented with it a lot, but you could probably figure out a good use for that in terms of a game where maybe you want to move precisely on surfaces that have different materials, like icy surfaces or whatnot, and have it apply it in a very physically realistic way. Another few things that we have here in our play scene, we have a dungeon generator object. So this dungeon generator object is just an empty object with a level generator script here. And then we have a few other objects, a floor parent, a walls parent, and a whisper source. So we'll get into the details of what all of those mean. Our goal today, we'll be talking about a few things. So we'll be talking about, here's a picture of just our maze. So we talked about some of those things at a high level. We'll actually explore how to implement them in Unity today. So making a maze, making the fog effect, walking through it with our character controller. We want to be able to have some kind of gameplay here. So we have collectibles in the form of this red coin. It's actually part of another standard assets pack, the prototype assets pack. It comes with a prototype little coin object that you can throw in. Anybody notice anything about this coin beyond the fact that it's just a sort of red coin? What else do you notice about this scene here? It's emitting a glow. Any ideas as to how it's emitting a glow? It's a light source inside of it, exactly. So we'll talk about that. We'll show you how that's implemented. Very easy to do in Unity. And then we'll also talk about, towards the end, our 2D scene, our title scene, and how to construct it, which is actually very easy in Unity as opposed to doing something by code. You very rarely actually for interfaces need to touch code, at least in terms of how to lay them out. In Unity you can do everything very visually and with the mouse, and it's a pleasure to make interfaces if you're used to just making them in code. So texturing. So last week or 2 weeks ago we did nothing with textures. It was, well, that's not true. We had one texture on the background, which was the sort of scrolling background, but we didn't really look at that too much. In today's example, the helicopter and the coin and the buildings and all that stuff, those were all just polygons with flat colors associated with them. Today we'll be talking about how to actually texture things with materials. And so this is very easy to do in Unity. So I'm going to go over to my title scene here, just because it's it's lit in a fairly normal way as opposed to the play scene, which is not lit in a normal way because we're using environment lighting and we don't have a skybox. The title scene has a fairly normal lighting setup. So if I add a cube here to the scene, so you can see right off the bat, by default, we do get a material here, which has what's called an albedo component. Albedo just means like what's its surface color look like. It has a much more technical definition, and you can look up on Wikipedia what albedo means. It has something to do with the way that light interacts with surfaces. There's a lot of other elements here. You can make something look metallic. You can make it look smooth or rough, and you can also add normal maps, height maps, and a few other things, which gives it more of like a bumpy texture and so forth. And you can also make things emit light this way, which the coin actually not only emits light, but also is a light source, so it does both. And there's a few other things here. For example, let's say you have a very large cube and a small texture. If you put a very small texture on a large cube, what's it going to look like? What's your instinct? If we have a very large cube, but let's say we have a 64 by 64 pixel texture, but our cube is humongous, what effect is that going to have on the cube? It's going to look kind of like an N64 cube, right? It's going to, what basically happens is it's going to interpolate between the texture pixels, the texels, when you apply a texture to your cube. And so when you apply a small texture to a large surface, it's going to look stretched. It's going to look stretched and like it's going to look also filtered, like you sort of see in some YouTube videos. If you watch them and they're recorded at a very small resolution, but you blow them up, they look filtered. Or if you've ever stretched a picture in the right software and it looks interpolated and filtered, it's going to have that look. So what you can do is you can apply tiling. So here we can see there's a tiling element, X and Y, so of 1. In the X and Y direction, because it only applies on a flat surface. So the effect of tiling would be such that if you have a 64 by 64 texture, you could just tile that texture several times to get the desired look that you want on whatever surface that you're trying to look at in your game world. Maybe it's a very small object, but maybe it's a very large object that you're looking at as a character, and you want to tile bricks, for example, or stone. So to apply a texture to a 3D object in the scene, I'm going to go into here. So you need a material first. And so these are all Unity material objects. You can tell because they have a circular, they look like as if they've been wrapped around a sphere. These are all Unity materials as opposed to textures. Textures are just 2D textures, 2D images. So this is part of an asset pack that I downloaded for this lecture called Dungeon Modules, Low Poly Dungeon Modules, which is in the asset store. And so what I'm going to do is I'm just going to apply, let's say I want to just apply this rock material to this object, right? And I go over to that. I'm going to first add I think because I went into the material, had a incorrect appearance. So do that. Oh, that's strange. I'm going to create a new scene. And then I'm going to add a cube, and then not pot, but maybe the beam. I wonder why it is not. That's very strange. For some reason, it might be a setting that I have enabled that's not allowing it to correctly render. But the effect of that should be that we apply, normally if you apply a texture to a material, it'll have the effect of creating, it'll instantly texture it. But what I can do is I can go to textures here, and this should work too. I can go to that, and then it'll apply it that way. So normally, if you're in a fresh project and you add a new 3D object and you just click and drag a material onto a 3D object, it will texture it for you. In this case, I think because it's automatically assigning a material to these objects based on some project setting that I'm off the cuff just unable to, I don't know for sure. You can instead just go to the albedo component here. So albedo functions not only as a color, but also as a texture for your object. And so you can apply a texture, just a 2D image, to your albedo component of a material, right? And that'll have the same effect as texturing it immediately. So normally what this is supposed to do is create a albedo, create a new material with that texture as the albedo when you set a material to the 3D object. Now, I wonder if yeah, I'm not sure. I'm not sure exactly why it didn't work as like right off the bat like it's normally supposed to. In a fresh project, it will. I'll try to investigate. But if it ever happens like that, where for some reason I think it has to do with the way the shaders are set on here. Maybe there's a setting I'm just not sure about. But you can just set the albedo component here manually, and it'll have the same effect. So the albedo component of your material, setting that with a texture, textures objects. And so that's effectively how we get from this sort of look of a flat shaded or flat color shaded object to a texture shaded object, just like that. And texture mapping, sort of in itself, is a very wide field and fairly complicated, but ultimately it looks something like this. So can anybody tell me what this looks like here? So we see here, obviously, we have a fully textured model. But if we're looking at this, what does it look like we've done here? So what does it look like? Ignore all the lines, but what does it sort of look like we have on this surface? It's just a texture, right? We can see, we can sort of see the colors here. For example, maybe his belt here, or actually that looks like the top of his head here. This being the top of his head, and then we have like his belt and other things. This right here, we can pretty clearly see that's like sort of his face mask, right? But it's just on a 2D surface. Like this is just a regular texture. And so what we've done here is basically taken all of the polygons that comprise the model and sort of laid them out flat, right? We lay them out flat as if on a table where our texture is, and that's what UV mapping is. And this is usually something that you do in whatever 3D modeling software that you're using. In Unity, when you apply a texture to a material, or a material with a texture to an object, it will use its standard, it has its own built-in like mapping algorithm that'll apply material to a model. And so it does it differently for different objects. We can create like a sphere, for example. Move the sphere over here. And I'm going to try again and just to see if applying the material works on that. No, it doesn't. So so if you go into this material here, which is for some reason grayed out. New scene again. Create a new 3D sphere, and then oh, this time it looks like it's, oh, I can't tell. No, I don't think that's working. Oh, now it allows us to accept a texture. Okay. So we can apply a texture, whoops, we can apply a texture to that. And so now we can see our sphere has been mapped as well. And it looks fairly convincing. It's been wrapped around it in a way that doesn't look too distorted or too weird. And so Unity has its own ways of mapping for its primitive objects, whether it's spheres, cubes, we have a few other ones, capsules, cylinders, planes. And it'll depend obviously on what your texture is. If your texture is fairly ornate, it might end up looking distorted. But for most purposes, for simple primitive objects, for most textures, it should work pretty well. Now, if you imported a model that was like a table or a character, and you just applied a texture to it, it's not going to look good. It's going to look messed up. And so your 3D software will export a material with the model, assuming that you've modeled in that software with a texture. It'll actually give you a material that you can then reference that will properly apply a texture to your character, but the same sort of apply a texture, just a regular texture to a complicated model, just isn't going to work because it hasn't been UV mapped in a smart way. Unity's not going to know, I have a table, I want to map the texture to the table in a way that looks convincing. You can see this kind of if we create a cube, and then if we go ahead and, I've been making it apparent for some reason. If we go up here, I'm going to first assign, OK, for some reason that worked instantly. But you can see we've applied a sort of wall texture to it. And then if we scale it down, so this is the scale button up here. So we have, you can move, rotate things. If unfamiliar, the sort of these top buttons up here are transform operators. So you can move things, scale, rotate things, and scale things. So if you scale this along the, this y-axis a bit, and then you zoom in, the texture looks pretty compressed and distorted because it's just doing the same algorithm and assuming it's the same kind of surface without taking into consideration how it's been warped, right? So ideally, you wouldn't have these sort of like flattening thing, this flattening happening. And so in your 3D software, you would unwrap your model and then apply a texture to each separate polygon of your model in a way that looks convincing. And so this isn't anything that you necessarily have to do for the lectures, or for the demonstration, for your project. But if you are creating your own 3D assets, if you're importing 3D assets, and if you want to use textures in a way that we're doing today, you will need to probably become familiar with UV wrapping, UV unwrapping, UV mapping in whatever software that you're using. And if you're just unfamiliar with it in general and have wanted to know sort of what goes on in turning a flat white polygon character into something that has a texture, this is effectively what happens. You unwrap it, make it flat, sort of like stamp the material onto it effectively, and that maps the UVs of the texture, sort of the texture's virtual coordinates, to your 3D model. So any questions as to how this works at all? Or about Unity and applying textures?
What's the general way that you make the textures on the right, where it's kind of like, it's like a world that's been flattened?
How do you make the textures on the right? That's kind of an art form in itself. You do have to do it by hand, and sort of know. There's a good amount of trial and error that'll go into it too, as you're making your model and sort of unwrapping it and noticing, oh, this looks weird as I'm applying this polygon to this surface. I'm going to go ahead and change that texture. But you could use GIMP or Photoshop or any standard texture creation software, and kind of just, it's something, I don't do a lot of it, but it's something that I imagine that you just get better at with time, and artists, texture artists and modeling artists probably develop sort of like an attuned sense of what makes a good texture versus what doesn't. Generally, you'll make the model first, and then you'll make the texture. OK, so we already talked a little bit about about materials. We'll go back over it really briefly again. There is a resource that I really like and I think does a really wonderful job of teaching far beyond the basics of Unity, and that's catlightcoding.com. And it's totally free. They just have a bunch of free articles on there, which are very in-depth. And this is a screenshot taken from one of the articles where they talk about how to make really interesting materials. So you can see here, this one on the left, it looks very, it looks like a fireball, like it's made out of magma. And it's got bumps on it. It has contour. You can see that there's sort of like a glow to the fire on it. On the right, you can see that this model has sort of conditional shine on certain parts of it. Like the metal part of it is shiny, but the rest of it isn't. And sort of like, how do we make certain parts of the material shiny? How do we make certain parts of it flat? The article goes into depth on that, and effectively what they do is they use several layers of maps, like a shininess map, which is a texture that tells that you reference in a Unity custom shader that you write, which the article teaches you how to write, which will make certain parts of the texture glossy and certain parts of it not glossy, so matte. And so you can do a lot of really cool, very interesting things, and Unity's shading system is very sort of the sky is the limit. Because it's effectively a standard shader language, like it's effectively the same thing as HLSL, I believe, which is high-level shading language, which is if I'm not misremembering, Microsoft originally came up with it, and it's very similar to GLSL, which is the OpenGL shading language. And so what these are effectively is just little programs that run on your graphics card. We talked about this before, but they tell your scene how to process lighting for the objects that are within it. And everything in Unity has a shader associated with it, even if it's just the standard shader, which by default is just a white color. But you can write your own shaders, and you're capable of virtually unlimited possibility. And this effectively is all a shader, and it's all a shader that's been written in code, but we have a lot of these variables that are exposed to us, and albedo is one of them. And albedo is sort of conditional. If it gets a texture applied to it, it will just render that texture. But if you apply a color to it, it will apply that color to your material. And so that's how you can get, textured things versus non-textured things. Metallic just computes shininess and reflectivity off of surfaces, and that's just something that's written into the shader and produces the lighting responsible to make that happen. And all of these different things are just part of a single shader, and a material is effectively a shader. They're kind of one and the same. A material is a little bit different in that you can also specify how its surface should interact with other things. So for example, if you're in an ice level, a material can not only be like the sort of glossy, icy look of something, but also how slippery is it when I walk over it, and should I slide, and how should other things interact with it that have physics. So like those two sort of hand in hand are sort of what a material is. But likely as you're starting out, the only real things that you'll need to consider, and you're sort of bound only by your curiosity, are albedo and maybe metallic and maybe emission, and then depending on how big your thing is and how small your texture is, maybe tiling. And then recall last week we manipulated offset. So offset is how much the texture is shifted, and recall it loops around back to the other side. And so by manipulating offset on the x-axis, we were able to get a infinitely scrolling texture, right? And so all of these things have their uses, and pretty much everything in Unity has its uses. It's a very vast toolkit to use, but those are probably the important things that you'll see. And this article and many others on this website, which I highly recommend if you're looking to get really deep into Unity, will give you a lot of insight into how things work far beyond just the surface level there. So any questions on materials? All right. So we're going to take a look now at lighting. So materials are one part of the equation. So that sort of defines how things should look when light hits them. But we also need light itself in our scene to illuminate things. And so this is taken from another article on cat-like coding on rendering. And so this is a scene with a lot of lights, a lot of glowing lights, emissive lights. And there's a lot more going on here. But this is another great series of articles on how to understand the lighting model in Unity. And it teaches you a lot. It teaches you almost down to the very bare ingredients of the sort of the software and the rendering if you want to go that deep. I certainly haven't gone through every article because there's just a tremendous amount of content. It's very deep. But if you're looking to really get a sense of how it works, I would encourage you to explore that. So we'll look at a few different types of lighting. Beyond the more complicated things that this article talks about, we'll look at the different styles of lights, which you'll probably use more often as you're starting out. So point lights. Anybody have an idea as to what a point light might be based on this picture?
Pointing in a very specific direction.
It's not pointing in a very specific direction. That's actually a spotlight. So a point light is a source of light that actually shoots out in all directions around it. So it emits light in all directions, but within a confined area at a specific intensity. A spotlight shines light in a specific direction, so only one direction. And what's interesting about spotlights is you can actually apply what's called a cookie to them. And what a cookie does, very similar to what the Batman light does, it allows you to apply a texture to a light and therefore cast shadows, specific shadows on the light. So if you wanted to make something like the bat signal, you could put the Batman icon cookie on your spotlight, and that'll shine the light, but the Batman logo will be in the middle of it. It's effectively the same thing as taking a literal spotlight and putting an object onto it. It produces a shadow, a manual shadow. It's called a cookie. Yep. A directional light. So anybody know what a directional light is? So despite its name, it's actually not the same thing as a spotlight. So directional light, we used a directional light last week, actually, last lecture. Directional light casts light in a single direction, but throughout the entire scene, as if it's the sun. So this allows us to illuminate globally the entire scene, but all light gets cast from one direction. So if you want to produce the appearance of daylight in your scene, just a single directional light will illuminate everything. And then the last thing, which is used less, is called an area light. So does anybody know, can anybody guess what an area light is based on this picture here? Yes?
So it's light that's only on the surface?
Light that's only on the surface. Kind of, yes. So it's light that will emit from the surface of a specifically designated rectangle, effectively, in one direction. So you can define a large area, for example, maybe you want like a wall strip in your game or something along the wall to emit light specifically to the left or something like that. That's what an area light is capable of. Now, area lights are computationally expensive, and so you can only use them when you bake your lighting. Does anybody remember what baking means when referring to lighting? So baked lighting just means that instead of real-time lighting, calculating things dynamically, the light gets calculated one time and saved and almost like freezed onto all of the objects in the scene. And so there are pros and cons to this. What's a pro to baked lighting, do we think?
It's less computationally intensive.
Less computationally intensive. What's a downside to baked lighting?
Can't be dynamically affected.
Can be dynamically affected. So if you're walking through a baked lighting scene and you're expecting to cast a shadow on something or for something to cast a shadow onto you, it's not going to happen because the environment's already been, the lighting for that scene's been pre-baked. It's almost as if we've just recolored the world in a specific way, but we're not actually doing any lighting calculations. But this is how lighting worked in like the N64 era, and it's how it still works now for certain situations. If you know nothing's going to cast a shadow on something, you can make really nice looking lighting for a scene without needing to do it in real time. You can just bake it, right? So those are the different types of lights. So we can see that in Unity. So if we go here, I'm going to, so right now we have a directional light. So this directional light is this object here. By default, and you can zoom in as much as you want, but it's sort of like, oh, there we go. This directional light is only shining in one direction. So I can move it here. So currently I'm in, it's a little bit weird to navigate just because it's been rotated a little bit. Given that it's a directional light, its rotation. So notice how it changes. So if I shine it upwards, notice that everything becomes black because the lighting is just shining upwards, right? It's as if it's coming from below. And if I shine it towards there, notice that the lighting on the sphere and the little cube there sort of change a bit, right? Because they're getting affected by the direction of the light a little bit. But they both get affected the exact same because the directional light is omnipresent. It's throughout the entire scene. It's a global object. Now, if I delete the directional light, notice we have no light now. So these things just look kind of like statically shaded. You can add a new light through, if you right-click in your sort of game object view, and then you go over here, you can see we have all the different lights we talked about. There's also things called reflection probes and light probe groups, and those are a little bit more complicated, but those allow you to effectively get pseudo real-time lighting and reflection with baked lighting and reflection. We won't talk about those in today's lecture, but here's a point light, for example. So let's see, where is it? Oh, it's right over here. So I'm going to move it over here. So you can see it's not global like the directional light was, right? It's just affecting this very limited, and I'm going to zoom in a little bit so you can see a little bit better. But it's affecting just sort of these two objects relative to where its position is, right? And so this works perfectly for things like lamps in your scene, if you want to have a street light, or whether you want to have maybe like a fire going on in a house, or if you want the, like the power up that we had in the, or the pickup that we had in the Unity scene, right? We have just it's just emitting a purple light that is within a very small radius. Notice here, we can change the color of the light. So if I make it like that, for some reason, oh, here we go. So we'll do that. So notice now it's emitting a purple light. So you can color a light however you want to produce whatever effects you want. So fire is not going to emit white light. It's probably going to emit like an orange-red light. Street lights are probably going to emit kind of like a yellow, orangey light. So depending on what your scene looks like and what you're trying to emulate, you can accomplish pretty much anything with just these very simple objects. So I'm going to get rid of the point light, and then I'm going to create a spotlight. I'm not going to create a area light just because we need to actually bake the lighting into the scene, but I will create a spotlight just so we can see what it looks like. Get it in the right position. Sometimes it can be a little tough to figure out exactly where you are. Okay, getting close. There we go. Perfect. So this little spotlight right here is being produced by our object. So you can see we can move it around, and then we can apply a cookie to it if we want to as well. It's right here. So if you're in a spotlight and you want to apply a texture to it, just this little cookie, and it just expects a texture. So whatever image you want. And if you're creating a cookie texture, white means full light, and black means full shadow. And so you can make it a grayscale image. You can make it anywhere in between white and black, which will allow you to produce some interesting effects. For example, the manual in, it's not here. I didn't include the picture here, but the manual shows like there are some kind of like the lights that you put on a stand, and they have a bunch of LEDs, right? And they're sort of in a grid, and they shoot out a spotlight. You can create a cookie that's kind of a grayscale with those gridded lines, and it'll shoot light onto the scene as if it's being broadcast from a sort of grid of LEDs. So there's a lot you can do with just some very simple ideas. Those are the kinds of lighting that we can use, and in today's lecture we only really use the point light, and in last lecture we used the directional light. And spotlights, you could, for example, programmatically change, for example, the rotation of a spotlight. If you want to have like a swinging spotlight in your scene to illuminate some wall or some surface, there's a lot of cool things you could do with it. So those are the core types of lights in Unity. Does anybody have any questions as to how they're used or how they work?
For the directional light, does it matter where it's placed or only the direction it's facing?
It does not matter. So for the directional light, it does not matter where it's placed. You could place it anywhere in your scene, 0, 0, or some far distance away. It'll have the exact same effect on the entire scene. Yeah. Any more questions? Okay. Cool, cool. So those are lights. Bump mapping, talk about very briefly. So bump mapping is, we actually do use this in the game. A bump map effectively is, so what you see here on the left is an actual 3D scene. These are actual models being shaded in real time. Not in real time, but they're actually real models being illuminated. In the middle, we can see what's called a bump map. And on the right, we can see just a flat, like a flat plane with a bump map, with that same bump map applied to it and then illuminated. So what a bump map allows us to do is to take a flat wall or flat surface or whatever you want and then simulate like an actual three-dimensional contour, three-dimensional bumps or whatever you want on that surface without needing to create the actual geometry to make it possible. And so there are different tools that will allow you to create bump mapping objects, or bump mapping textures. Often 3D packages will have these, so you can create them, or other software. But they are effectively just the encoding of what are called surface normals. So just a vector going from outside of the polygon at that given point, and they tell the lighting system in Unity, pretend as if there's actually geometry pointed in that direction when you calculate it. And so even though it doesn't distort the geometry in a way that's like this is still completely flat, the lighting thinks that the geometry is kind of, contoured. And so it allows us to create, this is kind of a toy example, but it's actually relevant in the case of walls that have, and we covered this last week, just not in as much detail, but walls that you want to be flat and you don't want to have a lot of polygons for, you can create a bump map for and apply that bump map, and then when you're rendering it, when you walk past a wall, it's going to look as if the wall actually has cracks and bumps in it for a realistic effect. And this is used in the game to a slight degree, and you can crank it up if you want to. I didn't on my computer because my settings or my specs aren't sufficient, but every texture in today's example has a bump map associated with it, so you can actually see what the you can actually see the effect of bump mapping at various degrees of use. The materials here, so I'm going to load up the scene that has the actual stuff. And I'm going to, actually I don't need to load up the scene. All I need to do is go to the materials and the floor, for example. Where's the floor? Right here. So notice that before we talked about albedo, and then I also mentioned normal map. So right here, all you really need to do in order to get Unity to detect normal maps, and this is just part of the standard shader. Normal maps and bump maps, by the way, are effectively synonymous. You can just drag your normal map texture into this field here, this little square, and then give it a degree at which to apply that normal map. And so if you look at this here, we might be able to see, I don't recall, yeah, we can sort of see how it changes the texture, right? So at 0, there's no normal mapping taking place at all. That texture is just completely flat, as if we had done just the regular apply a texture to a sphere. But the degree at which we apply normal mapping, so notice at degree 1, it kind of looks pretty realistic, as if we've got kind of a stony texture. And the more we go, right, the more exaggerated it starts to look, right? And you can just keep doing that, and it'll eventually just look really distorted. But that allows you, and depending on how strong your computer is, you can go higher or lower to affect just how bumpy, just how strong the bump map, the normal map, affects the lighting rendering. So it's that easy to get just a fairly sort of extra sense of realism in your scene. So you'll notice if you're walking through the scene, if you turn off lighting, it's even easier to see all of the surfaces, the floors, the ceilings, and the walls have a bump map as well as a texture map. So that's, in case you're wondering what these weird colored textures are, RGB are XYZ for the surface normals and their permutations thereof. And that's how it gets encoded into this. And so often you can see, if you're looking at a bump map and a texture map, you can kind of see together, like, oh, okay, this makes sense. The parts that I would expect to be bumpier do have a correlation to how they look on the actual bump map texture. You can see it here. Everything that is bumpy or contoured is very visible in the bump map. That's just by nature of the way the data is encoded. So any questions as to how bump maps work or what they are or how to use them in Unity? All right, cool. So now we're going to start getting into a little bit more into how this all comes together in our maze, on our game, and we'll talk about maze generation. So I'm going to just start up the the scene here. So I'm in the actual play scene. So in scenes, I loaded up play as before. I'm going to hit play. I'm going to turn off my sound just because the creepy sound is a little disorienting after a while. And then I'm going to, I'm going to go to a 2x3 view and then hit play. So we have the regular game view down here below, and then also, if I zoom out, you can see that our scene was empty before, but now we've got a maze. And currently it's not very visible at all because, one, we're applying fog, right? And recall, fog allows us to effectively add color to objects that are farther away from us. And two, there's a ceiling on top of our, a roof on top of our maze, so it's actually blocking out the actual what the maze looks like. So we can fairly easily make a couple of changes here in order to see our maze a little bit better. So I'm going to go to Window, I'm going to go to Lighting, Settings. And so if you go to Window, Lighting, Settings, those are your sort of global Unity lighting settings, right? You can set your skybox, you can set environment lighting, you can set things like fog, you can choose how things are baked. There's a lot of things here. We won't cover nearly all of them. We will cover a few of them. Environment lighting is a big one. That's actually how we're lighting the scene in this game. So all of the lighting that's not, all of the lighting is environment lighting. That's how we're doing it. We're doing it with color. So notice that you can choose skybox, gradient, and color. So if you choose skybox environment lighting, it's going to have sort of like, it's going to look kind of like this skybox that we have here, right? This sort of in the far distance looks blue, kind of looks a little bit more natural. But when it's applied to our scene, it doesn't look quite the way we want it to look. So what we went with instead was just color, and I chose this sort of murky, greenish, brownish color, and that gave the result that I was looking for. But you can make this any color you want to. We could make this some sort of bright yellow color. I have no idea what this is going to look like. This is probably going to look horrible, but yep. I mean, actually, this in a weird way, this kind of looks interesting. This actually looks closer to the original Dreadhalls game than what I did, but it's not very scary. Kind of looks like we're in a pyramid. That is, am I able to go back? No. Okay. Well, I screwed up the color. Let me try and find kind of what color I had before. It's kind of like a nasty green. Kind of like, nah, it's probably good enough. Okay, something like that. And so we play it again, we could see, we're back to the nasty dark color. But that's environment lighting. So it applies a lighting uniform, just ambience, kind of like a directional light, but it doesn't have a direction. It just applies to everything in your scene at a given intensity. And that is how we are lighting our scene. It's that easy, just environment lighting in our scene and our lighting scene window. Now, the other important thing here is the fog. So fog is almost as easy as just clicking this button here that says fog, and then choosing a color for it, probably. You can choose the density. So obviously, if it's a higher density fog, it's going to look as if you're in a foggier place. Like it's going to sum the color to things that are closer to you faster than it would if you had a lower density fog. And there's some other features here, some of which I'm not terribly familiar with, but for the sake of today's example, just make sure fog is selected, and then click, make sure you have the right color for your fog. So if you have like a ridiculous red color for your fog, it's probably going to look weird. Yep. But you could see how you could do all kinds of weird effects just by adding these things together. Like if you want to have the effect of being in some sort of like, I don't know, noxious foreign world, maybe you want like a purple fog instead of like a dark green fog or whatever. That's, it's super easy. You produce a lot of very basic but effective effects that way. I think it was just kind of the same nasty green color. So to bring up this lighting screen, all you need to do is, if you're on a Mac, I think in Windows is the same thing. There's a window option in the top menu. Window, and then lighting here, and then settings. And so this will bring you to all of the settings that are pertinent to at least today's example. And so we're not using any lights in our scene that we talked about before, at least for the lighting of the scene itself. Now, there are point lights being used for the pickups, and I'll show you that in a second. But what I wanted to illustrate was how we can sort of look at our maze after it's been generated. And so what we need to do first, notice that before we were kind of, we couldn't really see our maze at a distance because it was just purely dark green because of the fog. It was adding green to that geometry because it was so far away. So I'm going to disable fog for now. It'll actually remember your settings, which is kind of nice. So just going to disable fog. And I'm going to actually add a directional light to the scene. So I'm going to go here, add a directional light. And then I'm going to hit play again. So now our scene is lit. And it looks a lot different, a lot less scary. And we can see our maze a lot better. We can actually see that it is a collection of blocks. It's tiled blocks. Now, we can't see into the maze because the maze has a roof. So what I did was I just made generate roof an option in the script. And so if you unselect that and then we try again, now we can see our maze. So this is what our mazes look like. And so the cool thing about Unity, which I really love, is just this ability to look through your scene independent of the actual game, just to like help debug. Like, it's hard to know if you're generating your maze correctly when you're creating it in 3D. You know, in 2D you can easily just look at it, but in 3D, especially in a first-person game, you can't really see it. So being able to split your view like this, the scene and the game, and actually see, oh, my algorithm's working or it's not working. It's super helpful. So we can see that it is carving a maze for us. It looks a little bit weird. It's not a traditional maze in the sense that it has the classic maze shape to it, but it effectively functions as a maze, and it works very well for its intended purpose. And the algorithm is incredibly simple, and we'll talk about that. So that's our maze. I'm going to go ahead and revert all of the, I think if I just reload the scene, it should just revert it. Don't save. Yep. OK, so everything's been reverted, all the lighting, everything. I'm just going to do a sanity check and make sure. Yep, everything works perfectly well. So anybody have any ideas as to where to get started if we were to implement a 3D maze?
The way I did it once before is you put a bunch of X's where you want something to be drawn in an array, and then you loop through the array and draw, instantiate the walls.
Yes. So create an array, populate it with X's where you want, data wherever you want something to be instantiated, then loop over it and instantiate everything. It's exactly how it works. Now, in terms of actually creating the maze, do you have any ideas as to how would you go about implementing a simple maze generator? And there are obviously very complicated maze generation algorithms, so like nothing terribly fancy, but just a simple, how would you make a maze?
So it's random? Or
it's random.
Oh, so it's random.
So starting with the idea that we have an array, right? It's got to be a 2D array because we have two axes upon which we're generating things here. Even though we're in a 3D environment, we don't need a 3D array. We just need a 2D array. Because if there is a positive value for wherever we want to generate a block in our 3D array, or our 3D maze, we just generate a column of blocks. We don't need to worry about a third dimension, right? Our maze isn't like taking into consideration like multiple levels, at which point we would need to maybe consider 3 dimensions. I mean, even still, you can still divide those into separate 2D arrays of mazes. We just have an X and a Y. So how would we get started? What would we start populating the array? Let's say we have an array. It's just a bunch of zeros, right? What are we populating with the array after we've initialized it?
Maybe you would kind of start off with just full of walls and then add like corridors, maybe?
So start with a bunch of walls and then add corridors. That's exactly what we do. The algorithm is actually pretty simple. So I'll try and maybe draw a little bit just to see if I can illustrate how this works.
Make sure that you can get from one side to the other and there's no wall in between.
By making sure that every thing that you change is orthogonal. Every step that you move is orthogonal. That will ensure that you start at one point, end another point, and those points will always be accessible to one another, just by virtue of how simple the algorithm is and the orthogonality of it. So if we start with walls, so 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. These are all, in the distro, these are all Booleans because we only need zeros and ones, so we're just going to use true and false. We don't need to use integers for that. So this is our starting maze here. And actually, I'm going to add another dimension because, or not another dimension, but another size just because the walls always need to be there. These are basically untouchable. I'm going to try and draw that as best I can. Right? So we effectively have this as our working area for creating a maze, right? Because we want this to be, we want walls no matter what, because we don't want our person to be able to walk outside the maze or see the outside world ever. We want them to be locked in. So we have all of these ones here, these trues effectively, and so all we need to do is start like at some random position, let's say this value, at 3, 2, or well, it's actually technically it's 2, 3, because we index at y and then x in a 2D array. So we go 2, 3, we go here, and then we basically can move either left, or we can move either left or right, or up or down. Well, we can't move both at the same time. And why can't we move both at the same time? Let's say first of all, let's say we're going to carve our way through the maze, right? So we're going to turn these ones into zeros, but we can only move orthogonally, meaning left or right, up or down. We can't move diagonally. So we can only, let's say we have an x move, right, and a y move. And those can be set to, but by default, there's 0. So we're basically saying, where on this step of the generation are we going to move? And actually, technically, it's direction, because the way that we do it is via directions. Yeah.
So if you're moving down, then what's in front of you will have no wall. And there'll be walls on either side of you except for where you came from.
Yes, so if you're here and they move down, this is going to be 0, this is going to be 0, and so those points are linked.
Right.
And then from there, we're going to move in a given direction. And so all of those, let's say we move here, all of those are going to be linked. And so if we move here, all of those are going to be linked. Just by virtue of the fact that we're moving orthogonally, we can't create a maze that's unreachable, because the way that, just by virtue of the fact that we're moving now orthogonally. Now if we move diagonally, if I were to move here, right, there's walls right here, and then 2 spaces there. That's not going to work, because we can't access that. We're going to see a cube here and a cube here, and we're going to see we won't be able to move diagonally through walls, right? So that's why we need to ensure that we only move either in the x or y direction, not both at once. And so what the algorithm does is it randomly chooses, should I move x or should I move y? And should I move positive or negative? So it'll do math.random equal, 2 equals 1. Effectively, in the code, it's random.value less than 0.5, because random.value in Unity gives you 0 to 1 as a float. So you say, if random.value less than 0.5, which is a random chance between true and false, effectively 50%, move in x or move in y. And then, same thing, but should I move in the negative or positive direction, right? So if I'm here, I'm thinking, OK, let's say x move or y move. It's going to be an x move. So I'm going to move either left or right. OK, so am I going to move either -1 or 1 step, 1 to the right or to the left, right? So if it's -1, then that's going to move to the left, right? And if it's +1, it's going to move to the right. So, I mean, that's the essence of the algorithm, just looped over a bunch of times. Whenever I move to another tile, turn that into a 0. So actually, this becomes a 0. Change the color. So this will become a 0, right? So that's now an empty space. And in the code, that instantly teleports the character to that space too. So we know that our character is always going to be in an empty space, because he gets placed in the first open space that gets generated in the maze. And so let's say x move is equal to -1 on this iteration. So let's say we're looping until we've cleared x blocks. So I want to clear, let's say I want to clear 5 blocks. So to clear equals 5, right? That's how many blocks. When we've cleared that many blocks, we're done with the maze generator, right? So cleared 1. So our current counter is 1. So x, we get flip a coin. We're moving to the x direction by -1. So we move 2 here, and then we turn this into a 0. Now, this implementation of the algorithm moves one step at a time. And so because of its randomness, what this ends up doing is it produces very large chunks of deformed space just because the crawler is just constantly moving around kind of like haphazardly. So what's a refinement that we can make to this algorithm to make it look a little bit more like corridors or like hallways?
Just keep going until you hit the other wall in the same direction.
You could do that, yeah, keep going until you hit the other wall. The result of that, you mean hit the side of the maze?
That's what I mean, yeah.
Yeah, because, well, if you did that, it would effectively just be like, it would kind of be, it might work in some cases, but it will be very long hallways and not a lot of like turns or anything like that. So the result, what we actually want to do is when we flip a coin and we say X move or Y move, we want to also say times to move. We want to create a new variable called number of times to move, effectively, right? To move. And then we just set that to a random number between 1, so we're going to move 1 tile, or the size of the maze minus 2, right? Taking into consideration both walls, right? So let's say we get the, let's say we did X move minus 1, and we only got to move equal to 1, right? So we only move here. We move once in this direction, so we've got 2 spaces. And then let's say we flip a coin again, and then we got Y move, right? Positive 1. And then to move, we got 2, right? So we're going to move 2 directions in the Y axis by 1. So what this is a result of us going down here. So we go 0 and then 0, right? And so the effect of this is that we move, we can move in more than just 1 block at a time and avoid the sort of random, like haphazard, weird, organic, large room aesthetic that we want. If we want like a hallway, grid-like, dungeon-looking like room generator, right? Now there's a caveat to this, and that is if we start here, for example, and then we want to, let's say we flip a coin, it's X move, but it's positive, like positive 4, right? We can't obviously move 4 tiles to the right because 1, it'll go into our walls on the outside, and 2, it's actually beyond the bounds of our array. So we need to clamp that value down. When we add 1 to our value, to wherever our X, we have to basically keep pointers, right? We keep pointer to whichever tile we're currently at. We need to keep, when we actually go to the next tile in our step, we need to clamp that value within the range of our walls. So we need to clamp between 1, so because we don't want to be at 0, we want to clamp it between 1 and maze size minus 2, actually, because we want to make sure that we don't go any farther than this one here. Does that make sense? This is how, that is effectively how our generator works. It's a step beyond just the move 1 block at a time, just because the mazes look way too empty and weird. With this approach, where you're moving in a direction and for a random number of tiles as opposed to just 1 tile at a time, you actually get pretty nice looking, simple mazes. This isn't how like actual maze generation works. For mazes that you would see in like an actual maze that you do on like a crossword puzzle book or a maze book or something. Those are more complicated. But this solution works well. It's very fast and very cheap, and actually pretty simple to understand. So any questions as to how the maze generator, the algorithm, at least as applied to our 2D array, works? All right, cool. That's basically the gist of it. So we're going to take a break here for about 5 minutes, and then as soon as we get back, we'll dive a little bit more into sort of how the character controller works and the pickup and a few other aspects of the game. All right, welcome back to Lecture 9. So before the break, we were talking about the way that we implemented procedural maze generation. So a fairly simple algorithm that creates this sort of hallway look where we can easily get lost, but they aren't technically mazes in the traditional sense like you might have seen growing up in puzzle books and such. Another pitch for Cat-like coding, because his articles are amazing. He has another one on how he did a maze generator, and in this one, beyond just regular blocks. Oh, I'm sorry, I didn't have the slide there on the thing. So this is a screenshot of another article from Cat-like Coding, where he talks about how to make his own maze generator. And the cool thing about his is that he has a bunch of different geometry involved in the scene. It's not just blocks. He has doors and windows and other things. And his algorithm is a little bit different than mine and produces some pretty interesting looking things. And you can see here also it has a view of the scene sort of superimposed on the actual scene, which he does with a trick using 2 cameras. So, also, here's another maze/dungeon generator article that I really like, where he creates sort of like Dungeons & Dragons style generators, and this is sort of pertinent to my interests as a developer because I really love roguelikes and dungeon generators and RPGs. But he goes into extensive detail on how to make a really nice and efficient 2D maze/dungeon generator that produces really nice looking dungeons. As you can see here, it's got a very variable layout, lots of corridors and rooms and stuff like that. So implementing something like this in Unity would be really cool. And there's a plethora of generators and assets like this that'll do the same kind of thing in Unity, available on the asset store. So you don't have to make this yourself most of the time. You can just go find either free or paid assets that will do all of this for you and save you a tremendous amount of time. And much of them are also very customizable too, so that you can tailor the generator to fit the domain of your game. So we saw how the lighting works in our game. We've seen the maze, sort of how it's generated, what it looks like. We have not taken a look yet at the character controller. So we'll briefly just take a look at that. It's actually incredibly easy to do in Unity, at least to get something fairly basic up and running. The way that we get a FPS controller in the case of our game is Unity has, which I alluded to before, a set of custom or built-in standard asset packs that allow people getting used to the game engine or just trying to bootstrap their game up and running with some very basic components, very basic things that are super helpful for just sort of getting your game running. So actually, we use the prototyping standard assets pack for our pickup. We use the characters one for the character controller, the FPS controller. So if you're in a fresh project and you just go to import package and you import this characters thing here, it'll import it into your game so that you can immediately use the prefabs that it gives you to create a character object. So it'll, by default, just put it in your assets folder underneath standard assets and then characters, and then there's a first person folder. And within the first person folder, there's a prefabs folder which has the FPS controller game object. And so all you need to do is just drag it into the scene, and then that becomes your default camera. So, sorry.
That comes with Unity? It's just
it comes with Unity, correct. That's just a standard asset.
and it's always in the prefabs folder?
It's always in the FPS controller will always be in the, so you have to import it first. You have to import the asset package, the characters package. Once you've imported the characters package, you'll go into standard assets. In your assets folder, there will be a new folder called standard assets. Within standard assets, you'll go to characters, then first person, and then prefabs, and then that's where you'll find the FPS controller. Yes, no problem. So the FPS controller, if we take a look at it, we talked about it before briefly, but effectively, it's just a capsule collider, which is sort of defying physics because it's kinematic with gravity applied to it. And it has a camera sort of on towards the top of it where the head is to simulate the perspective of somebody from first-person view. And there's some programming involved that allows you to control it with the keys and the mouse, to control the camera's rotation with the mouse and the position of the collider with the WASD keys. And if you want, you can dig into the actual script for it too. They're all included with the standard assets pack. When you import that into your project, it comes with all the scripts that make all that possible. I haven't dug through all of them in too much detail, but it's all there for you if curious as to how it works. And so if you want to get just a simple, FPS controller in your game, a character in your game to walk around and play a first-person game, it takes about a minute to get up and running. Now there's a lot of customization that you can apply to your character controller to make it not just the standard basic character, right? So you can set a walk speed, you can set a run speed, you can set jump speed, you can you can set the sensitivity of the mouse look on the game, on the FPS controller. You can apply what's called FOV kick, which means when you're sprinting, which it allows you to sprint with pressing shift, which multiplies your speed. It'll actually, I think it'll expand your depth of field a little bit to make it look as if you're kind of like claustrophobic, right? Like things kind of like go out, and so it looks more narrow, and it kind of gives you that look as if you're like sprinting down a path. And you can set just how much it increases by. You can set the curve of how that is applied here. So this is one of the components that Unity allows you to do is there's a curve object, and you can use this curve to influence various things in your game. I actually haven't used it much myself, but if you're looking for something to apply a curve to, Unity has an interface for making that visible within your inspector. Head bob, which means when I walk, should the camera kind of like go up and down. When you do have a head bob, like what's the curve look like? So here's another curve. This is the sort of what the head bob looks like, kind of a sine wave, but a little bit distorted. And a few other things. So for example, footstep sounds. Maybe you don't like the sounds that come by default with the controller, so you give it your own footstep sounds. Super easy to do. Just drag new sounds here. Jump sound and a landing sound, 2 more sounds that you can add to it. And that'll allow you to customize most of the feel of how your character moves around in terms of just a basic FPS controller. And so just by applying those very basic things, customizing them a little bit, we got lucky with this maze. This means that the maze went all the way around and then looped right back to where we were and ended there. So that's that maze. Okay. But I'm going to go ahead and turn up the sound. You can hear the footsteps, right? Along with the creepy whispering. But the footsteps are just provided to us by the FPS controller. And again, you can customize those to be whatever you want. And so this gives you the ability to walk around in your scene from a first-person view. It doesn't really give you much more than that. In order to do like an FPS where you have like maybe a gun or a weapon or something, you need to program some more things, and it's a lot more complicated. But for just basic navigation of a 3D scene, that's a great foundation, a great way to get started. So, any questions as to how the FPS controller works? There are other controllers too. There are third-person controllers. So if you want to use those, they don't come with a camera. Based on my experimentation, they don't actually come with a camera by default. So I think you have to parent a camera to them in the way that you want for your game. Like for example, some games have the camera super high above your character while you're walking around, and some of them have like a like behind the shoulder look, almost like Fortnite or Gears of War, like really close to the character. And then some kind of have, like in Banjo-Kazooie, you could be walking up a mountain, and then so the camera's kind of like perpendicular to where you are and sort of like follows you around. So camera programming for 3D characters is a little bit more complicated than it is for first-person games. And so that's why I imagine it doesn't come with a camera by default. So it can be a little bit more complicated. But I do believe there are a lot of assets on the asset store that can help bootstrap you for getting a programmatic camera setup going for your character in a third-person view. Yeah.
I noticed, like when you're walking around your maze, like occasionally you're like clipping the wall and kind of seeing like what's behind it.
Yep. That I believe that's a result of the collider being a little bit too big. So what he said was that walking through the maze, you can kind of clip through the wall a little bit. See if we can actually experience. Yeah, like right there. Yeah, and that's. I believe that's just the camera or the collider being a little bit too large, and so we could probably like get rid of that altogether just by shrinking the collider a little bit. Just a detail that I didn't iron out, but you'll see that in a lot of games actually. A lot of games have like clipping that you can get that you can observe depending on how they've programmed the game. But yeah, any other questions as to how character controllers work and like how the import process works and how to get it in your scene? Okay, cool. Yeah, it's super easy. Again, here's what the FPS controller looks like. Capsule collider with a camera. And then the third-person controller, by default, they give you a pretty nice-looking model on the left side there so that you can experiment with it. And then they apparently give you an AI one as well, so you can test AI in your scene with it. But I haven't experimented too much with that to vouch for how well it works. So an important aspect of today's example is that we've gone from having just one scene to having two scenes. So I want to illustrate how we sort of move between the scenes a little bit. And also, I realized we didn't really cover the dungeon generator in code detail, but notice that I have exposed a lot of things here: a floor prefab, wall prefab, ceiling prefab. These are just the cubes that are textured to be our floor, walls, and ceiling. We can just click and drag them from the inspector into our scene onto the components there. We have a character controller reference here so that we can place the character controller in our scene when we've generated the first block. We can basically take the transform and set its position to whatever that XZ is. And then a floor parent and a walls parent. So the reason that we have parent objects, actually, which we didn't look at before, whoops, I've lost track of where there it is. The reason that we have parent objects here is because when we instantiate all of the cubes in our scene, just sort of just instantiate them without really thinking about it, it ends up, basically, I'll show you here. Well, first of all, I don't know what this is. Oh, I think it's, that's interesting. Oh, because I clicked on the floor parent, right? Okay. So if you click on the walls parent, actually, I didn't do that yet, but it'll actually show you where all the objects that are parented or that are dependent on that parent. So the floor parent here, see how many floor blocks there are? There's quite a lot. Excuse me. There's a lot of floor blocks here, and in the walls parent, there's even more. There's a lot of walls and ceiling blocks. And if we just generate those without assigning them a parent, it'll just fill up our hierarchy there very messily, and it makes navigating our scene during debugging very difficult, right? We don't need to see that we have a million clones of the floor or the ceiling blocks or the wall blocks. And so what we do is we just take all of the clone blocks and we just parent them to an object. And when you parent something to an object, you get that little drop down. Like, for example, this first-person character, this FPS controller is the parent of this first-person character. And so those are two separate objects that both comprise the FPS controller effectively. A parent is top level, and its children are therefore within it, within this little arrow here, and it's collapsible. All of the things within the play scene, for example, the play scene is the parent to all of these. It's sort of like a folder hierarchy type of thing. And so if you want to clean up your scene, if you're instantiating a ton of things, just effectively containerize them by putting them into a parent object. And so we do that in our game with a function called createChildPrefab. And so what createChildPrefab does is it does an instantiation as normal, right? Creates a prefab, instantiates it, gives it a position XYZ, quaternion.identity because we don't want to apply any rotation to it, but my prefab.transform.parent equals parent.transform. It's effectively linking our, we're assigning the parent field of that prefab's transform to the parent's transform. And that has the effect of basically linking them together in a parent-child relationship. And that will allow us to collapse and expand a list. When one parent has a bunch of children, we can expand it and contract it in the hierarchy view and save us a bit of a headache in terms of navigating our scene when we instantiate a lot of things, which is fairly normal. So the actual I'll go over this fairly quickly. It's a fairly simple algorithm, and I talked about it on the screen, and we don't have a ton of time, but basically we go z to x. The reason that we go z to x is because in Unity, z and x are sort of like the ground axes, and y is sort of like the up and down axis. And so we don't want to instantiate, we're not really worried about navigating the y-axis during our maze generator, because all we're going to do is instantiate 4 blocks along the y-axis during that phase, right? So we're basically taking our 2D array, and we're iterating over it x, y, and then we're mapping that to Unity's zx, or xz. if that makes sense. Because notice like this is our ground, right? So where this transform is, you can see the ground, how this is x, the blue is a z, and y is this axis here. We're effectively only concerned about generating on the ground, and then when we generate a wall, we just generate it 4 blocks high on the y. We don't think about the y. So that's why x and y for our 2D array, but x and z for applying that array to Unity's 3D coordinate system. Does that make sense? Okay. So we're iterating over z and x, and then we're indexing into our map data, z and x, which is effectively the same thing as y and x. And then we are creating a child prefab if map data zx. So recall that our map data is a 2D array of booleans, right? And so if we have map data zx equal to true, that means there's a wall there. It means that there's a true in our array, so we should instantiate a wall at that location. So we create 3 wall prefabs, assign them to the wall's parent so that they get containerized within there so they don't clog up our hierarchy view. And then, let me see here. And so if we don't, so if we've gone through our maze, right, if we're generating our maze and we get to our first tile that's actually not a wall, so it's an empty space. So basically the else here, so if map data zx is not true, it's going to be false. So if that's the case, and if not character placed, so character placed is just a Boolean. It's a private Boolean. We don't want this to be visible in our inspector. There's no purpose for it to be visible in our inspector. This is just a Boolean for us to use in our script. So we set that to false by default because we haven't placed our character yet. But when we generate our maze, we have to make sure we put our character in a spot that there isn't a wall, because we obviously don't want him trapped in a wall or clipping through the maze, right? So if not character placed, we're going to set the character controller's transform. We're going to set its position and rotation, which is a function. We're going to set it to x and then y1 and then z, and then no rotation, so quaternion.identity. And then set that to true. So therefore, this will never be called again. So this only gets called in the very first empty space that we go through our maze. And that's it for that. No matter what we do, whether there's a wall in our maze or not, we're going to want to generate a floor and a ceiling at that space. So that's, of course, assuming that generate roof is true, which, recall, we made a public Boolean in our inspector so that I could debug and show you guys what the maze looks like from up above. So if generate roof, create a child prefab for ceiling prefab at x4z, so a bit higher up. And then no matter what, always want a floor, so create a floor prefab at x0z, so down below. And our character controller gets placed at, recall, x1z, so just above the floor. The assignment is actually, part of the assignment is generate a hole in the floor. And if there's a hole in the floor and the character falls through the floor or the hole, you should get a game over, right? So you're going to need to create a game over scene. We're going to need to transition to that scene. And then we're going to need to check to see whether the character's transform has gone below a certain amount, right? That's all fairly easy stuff to do. But you'll look to do some of that in here. And then the actual maze data function is here. I won't go over it in detail, but it's the algorithm that we talked about before, where we choose direction to move randomly, and we choose a random number of steps to move, clamp that value within the constraints of the maze, and then set every tile that we explore to false. And that has the effect of creating the maze. And then we just return that data back to our function. It's just a 2D array. Notice that in in C#, to create a 2D array, it's a little bit different than in a lot of other languages. It has its own set of syntax for that. You have the array syntax that you're probably familiar with, but then you also have this comma. And that comma is to designate that there are 2 arguments to that index syntax here. Just means an x should go here, and a y should go there, basically, or a yx. And that's 2D array. And you can make it as many degrees as you want to. Just add more commas to it. And notice that to actually allocate the memory that we want for that 2D array, new bool maze size maze size. So our maze is always square shaped. And you could easily make this maze X, maze Y if you wanted to make it like rectangular. So you just need to have 2 public variables instead of 1. And all of this is fairly visible through the inspector too. In our dungeon generator, you can see I made a tiles to remove 350. So that means that our maze is going to cut out 350 tiles. And as soon as it cuts out 350 tiles, it's done. And then our maze size is 30 by 30. So that means there's going to be 900 tiles in our maze. So you can tailor this to whatever you want in order to produce sparse or denser mazes to your liking. So any questions as to how the code for that works, more or less? So now we'll actually get to the scenes part of it. And so transitioning between, oh yeah, yeah.
I'm thinking like, for like a smaller game like that works great. But like for a larger game, wouldn't you want to model the walls as like 2D kind of objects and like the ceiling instead of like a whole cube?
Oh yeah. So for a small game, is it more ideal for the walls to be rendered as like one discrete object as opposed to like several cubes? Yeah, absolutely. That's 100% true. And actually, Minecraft is an example of this sort of idea that you think would work, but they actually consolidate all their geometry after they've generated it in this way and produce like models that are more optimized. Like that you think that you're interacting with this world that's a bunch of these little blocks all separate, but it's actually one big piece of geometry, and then it dynamically figures out what you're hitting and removes and adds blocks as needed. And there's some cool videos on YouTube as to how to do this in Unity too, which I looked at a long time ago, and it kind of shows you. You can actually dynamically create meshes and vertices and stuff in Unity and then create objects that way, which is really cool. But that's a little bit more on the advanced side. But yeah, absolutely. For an actual implementation of this, a simple but more efficient way to do it would just be to have like, one solid large wall object that's like as tall as you need it to be and maybe as wide as you need it to be for one character, and have that work. But for simplicity's sake and to illustrate the algorithm, we are just using the cubes. Yeah, exactly. But yeah, good point. That's 100% true. All right, multiple scenes. So the way that we do this, so I'm going to go into my text editor. Whoops. So the grab pickups script. So grab pickups is a component that's attached to the character controller because he's going to be picking up pickups. And what the grab pickup script effectively does is the character controller built-in has this function that you can define for it called onController collider hit, where anything that collides with the controller's collider will trigger this callback function. And you can grab the information about the object that you collided with and then perform some sort of logic on that. And so it's actually calling this function every single time we collide with any of the tiles or the blocks in our scene as well. There's just no logic to account for them, so it's just effectively an empty function call. But if it's the case that the game object has a tag of pickup, which we've set in our Unity editor, and I'll show you how to do that, then we should play a sound from our pickup sound source, and then we should, we actually used this in the last lecture, but only within the same scene. We're going to call scenemanager.loadScene play, and you need Unity engine.scene management using Unity engine.scene management at the top of your script in order to use this. And load scene effectively just will literally just load a scene by its name. And we're doing that in a couple places. So we're actually doing it there, but remember we had the title scene, which had the same sort of thing. You press enter and you load the play scene, right? So this load scene on input component that I created is attached to a text field in the title scene. And all we're doing here is in the update, we're just saying, hey, if input.getAccess submit is equal to 1, then scenemanager.loadScenePlay. Almost the same code. Only in this case, we're querying Unity's input. It has a global input manager, get axis. So it has several axes is how it defines it, different like methods of input. And then it defines them by keywords. So in this case, submit is a keyword, and you map those keys, or you map those keywords to specific keys and input sources on whatever platform you're targeting. In this case, submit is synonymous with either enter or return, depending on which platform we're using. And it could have other meanings if we're exporting this to Xbox, or if we're exporting it to the web, or if we're exporting it to a mobile phone. There's a lot of different ways it changes. And so the way that it checks is it'll be 0 or 1 specifically. So we can say if input.getAccessSubmit equals 1, scene manager load scene play. And it won't let you do if input.getAccessSubmit because it's explicitly expecting an integer, and it'll throw an error if you're trying to use it like a Boolean. So we need to use this equals 1 to test for equivalence. And that's all we're effectively doing there. Now, the interesting thing is when we reload the scene for the pickup, right, for the maze, there's a soundtrack playing in the background. And we want this soundtrack to constantly be playing the same thing and to loop, right? The sound effect. We don't want it to start up immediately again and start up like from the very beginning again. We kind of want this seamless sort of feel to it. And so how do we think we can solve this problem?
So it doesn't take any when
you reload the scene?
Sorry?
You don't want it to start over when you reload the scene?
Correct. So any ideas as to how we would do this?
For level 1 only in the beginning or something? Is that what you're saying?
Well, so whenever we collide with the pickup, we reload the scene completely from scratch. And so when you reload a scene, it destroys every game object in the scene, including all the objects that have audio sources attached to them. And so when it reloads the scene, it reinstantiates all the game objects in the scene, including those with audio sources, and re-triggers their playing. So what we want to do is prevent this from happening.
So just have a counter, and when you get the first pickup, then it goes to 1, and then you say if less than 1, play the sound.
That will have the effect of, so you're saying have a counter, and when...
Or true false would be, Boolean would be better at this.
So have a counter or true false. When you load the scene, it starts the music. But what happens when we reload the scene from scratch and the audio that was playing gets deleted?
Can you transport certain objects between scenes?
Can you transport certain objects between scenes? Effectively, you can. There's a function called don't destroy on load, actually. So with that, it's a Unity function, which allows you to preserve an object as it is between scenes. So if you don't want your scene with the music to, or your object with the music to destroy itself and then reinstantiate on load, well, technically just don't destroy itself. Just do don't destroy on load at the game object. And so this don't destroy, we apply this to our audio source, our whisper source it's called, in the scene. The only problem with this is if we reinstantiate, or if we don't destroy on load this object, it's going to persevere. But when we reload the scene, it's going to instantiate a new one. So what's the effect of this going to be? Going to have 2 audio sources playing at the same time. What happens when we do another one? You're going to have 3 audio sources playing at the same time. So for every time you go to a next level, you're going to add the same audio track to the scene. It's going to be very annoying very quickly. The way that we avoid this happening is by making what's called a singleton. And so what a singleton is a class that can only effectively be instantiated one time, right? And we do this by creating a static variable here called don't destroy. No, we called instance, which is of type don't destroy. So it's this component here, right? And so the don't destroy class as a whole has this static variable called instance. And we set it to null by default when we haven't instantiated a don't destroy component yet. And what this ensures in our scene, by the logic we have in the awake function. Awake is almost the same thing as start. It just means whenever you can pause an object and it'll awake from its pause state, but awake also gets called when an object gets instantiated. So if the instance is set to null on awake, instance equals this, so this don't destroy. So whatever this is being called from, this don't destroy will be the instance. Whatever the first don't destroy component is in our scene, the very first maze that we generate. The sound source instance will be this. And then we set don't destroy on load for the game object that is holding that don't destroy component, right? That audio source. But if the instance is not equal to this, so if we've awoken, and this is level 2, for example, instance is going to be set to the don't destroy component on the don't destroy on load object that we created in the first maze, right? Because we did this logic here. And so it's going to try and instantiate a second don't destroy component. It's going to another sound source. But instance is not going to be null. Instance is going to be equal to that first object. So we say if instance is not equal to this, destroy game object. So this is going to be from the standpoint of the second don't destroy that got created.
So the singleton basically persists.
The singleton will persist indefinitely upon its first instantiation, and there will only ever be one singleton. This is a very basic, very common pattern in software engineering for ensuring that you only have one object of a given type present throughout your entire project. But this is how we prevent multiple sound sources from being instantiated. We always ensure that only one object of that with that component gets instantiated at once, and any future instantiations of that object get destroyed immediately, assuming that they aren't that first object. If they are that first object, instance will equal this, and so it'll still skip this part, and so it'll stay alive. So any questions as to how the persevering through multiple scenes works for their sound source? Okay. That's how we get multiple scenes. So fog. We looked at fog already, but I have a few screenshots here to kind of help illustrate what fog has looked like over the years. So fog looks pretty unconvincing in this screenshot. This is Turok for the N64. It's just kind of looks as if, sort of at a certain distance, a very dense sheet of fog has appeared. And you can actually make this happen in Unity by setting the, there's a curve, a fog curve that I believe you can manipulate that will effectively, the algorithm that determines how the color gets summed to things far away is very fast as opposed to gradual or linear. So you can make it just like exponential effectively and make it look as if the fog is incredibly dense and starts almost at a very fixed spot and have the rest of this area sort of in front of you look normal. Here's another example, Star Wars Shadows of the Empire, one of my favorite N64 games, which has sort of the same look. And so in this area, you can see fog is very distinguishable, very artificial looking because it's very tinted. In this case, it looks very blue. In this case, it looks very like pale blue. This is Silent Hill, and Silent Hill looks realer, more realistic, but kind of the same thing at play here. You have a very pale gray metallic blue color, and the density in this case is very high. The density is much higher, well, maybe close to as high as it is in our game that we're showing today. But it's effectively the same thing, just with a different color. And they used it to great effect in here, not only for sort of this aesthetic to make you look as if you're in some sort of desolate town, but also to dynamically load objects or to prevent rendering objects that are a certain distance away and to optimize performance on the hardware that was severely limited at the time, which was PlayStation 1, which was a fairly weak console. And then here is Shadow of the Colossus for PS4, which just came out not too long ago, and we can see fog is still being used, but it looks photorealistic. And there's probably a lot more that they're doing. They probably have several layers of fog. They probably have textures and transparent objects that are simulating fog and a lot of more complicated things like that. Fog that only hangs at a certain distance, so it looks like fog going over the lake. There's a lot of things here, but it's the same idea, and they probably have the same sort of foundational base fog present throughout the scene. And then here's our game just to show how it looks like. You can barely even see it, but it does give you this sort of like lost in a really dangerous maze feeling, which and it's super easy to do, and it can save you performance and it can add a lot of aesthetic to your game. And so the last big thing we'll talk about today is Unity 2D actually. So I'm going to go back into questions about fog. I know that was a pretty high-level overview. We've already looked at fog. We've looked at how it applies in the settings. Any questions as to how it works or how to get it to work in Unity? OK. So we're going to go ahead and look at our title scene. And so we looked at this earlier briefly, but I'm going to go ahead and show you the components. So I'm going to take a look at our canvas. If you double-click on something, you'll zoom out. And so it'll automatically detect sort of what your resolution is and scale the canvas accordingly in your scene view. There's a 2D button here. I'm going to go ahead and go to my default layout. I'm going to click on the canvas. Notice that it shifted things a little bit because now I have a larger window that's going to be rendered to. I'm going to click on the canvas, and then I'm going to go to 2D mode. And then notice when you click on 2D and 3D mode, you go like instantly into like seeing it as if you're manipulating it in a 2D engine versus a 3D engine. And then going back to 3D, now it's a three-dimensional plane that you're actually looking at. So in 2D mode, you can easily sort of navigate it, right-click, and drag it around. I'm going to go here like this. And these are very simple components that you can just interact with as a GUI. Now, the main thing that you need to get any of this to work is the canvas, which is here. So if you right-click and then go to UI, you can go to Canvas if you want to, or you can just add any of these things that you want, and it'll automatically add a canvas for you, because a canvas is necessary for all of the Unity UI rendering stuff. So if I were to just add a text on an empty scene, it'll just create a brand new canvas and an event system. The event system is just how Unity talks to the canvas and all the UI elements of your canvas, given mouse and keyboard input and stuff like that. It's nothing that you necessarily have to worry about or use. But the canvas is the sort of overall container for all GUI stuff that you do. Now, if I click on the title text or the enter text, notice that they are children of the canvas. So they are within the canvas. The canvas is their parent. The title text, I can move it around. Notice that it snaps, right? It's got some nice snapping functionality. I can set it up there. It'll snap to the top. It's pretty handy. You can scale the bounding box. It doesn't scale the actual text, but notice that I do have like right justification, centering, left justification, those sorts of helping the sort of features. Right? I can increase the font size via a slider, right? So I can immediately see, without having to edit some code and then reload the project, what changing some of these values will look like. I can easily change the color in real time, so I can get a sense of how that looks. If you wanted some sort of slimy Dread50 look, I guess. And you can also assign materials to it as well, which is kind of cool, which I haven't explored too much in detail, but you have that option if you want to give it a material instead of a color, materialed font. Because ultimately, all of this stuff is still 3D, but Unity presents it in a way that makes it look as if you're interacting with it in 2D. It's pretty nice.
So you put it in 2D form, and when you hit play, it's going to open up to that?
Yep.
And then how do you transition to the rest of the game?
So the transition to the rest of the game is in the load scene on input here. So this script that we looked at earlier, so this is assigned to one of those text labels. So I just gave it to I forget, I think it's the enter text. So I gave it this load scene on input just because it's the enter text. It seemed appropriate. Could put it on anything in the scene. It doesn't matter. As long as it has this update function, which then has this if input.getAccessSubmit equals 1, and then recall go into the project settings, input. All these axes here are defined for you automatically, and then you can choose what they map to, but submit, as you can see, positive button is return. So if submit is equal to 1, when we press return, it'll be equal to 1 effectively. And it gets mapped to other buttons depending on what input sources you have on your device. But you can check what it is on your computer just by going to axes in your input manager. So it's, once again, edit, project settings, input, and then you can see all the axes here.
So the 2D scene, that's just a scene in itself.
It's a scene in itself, completely. It has a camera, so we are, the camera renders, the thing about Canvas is it's kind of separate from the camera, so it gets rendered onto whatever the camera is rendering separately. But the camera in this case what I've done, because if by default we just render the camera and the UI, it's going to look just like this. It's going to look like the sky with Dread50 and press enter. That's not the aesthetic that we want. So I take the camera, and then you can give it a background. So by default, the background is that sky, is the skybox. And so it set clear flags. Clear flags are same thing as background. So whatever there's no geometry or anything, this clear color, clear flag, this gets drawn to before any geometry in the scene, basically. Excuse me. So clear flags, solid color in this case, and then just black using a color picker. So super easy, super nice. And then this UI, this canvas, will get drawn on top of this camera. So that's what produces the sort of combined effect of having the UI text and then the black background. And then that enter text having that component that checks for the submit input, because that's what enter and return map to. That is what lets us transition from the current scene to the play scene. And so there are a lot of other cool features that these like labels and such have. For example, being able to set its anchor position. So depending on what device you're shipping to, you might want, you know you're going to have multiple screen sizes and screen resolutions. So you can say, I want this label to always be at the very top middle of my scene. And I can do this by clicking this little box here, which is the anchor point selector, and then just clicking that. And so that'll always anchor Dread50's text to the top middle, no matter what our resolution is. It'll always be there. And there's a lot that you can do on top of that. And you can do that with any UI component, just relative positioning depending on the resolution. And the nice thing about Unity 2, if you go to Game, you can actually choose, in the second menu, you can choose a lot of aspect ratios. So 5:4 doesn't look that great. 4:3 doesn't look that great. 16:10, 16:9, and then standalone. So standalone is the default export size of your platform. But you can choose, you can have it, you can test different resolutions, and you can also add more too. You can add a fixed resolution if you want, or an aspect ratio, and do a lot of cool things that way. So you don't have to necessarily test it physically on different devices, although it's very good too, so you can make sure that you're not blowing up your hardware, but you have that option. So any questions as to how Unity 2D works and how the canvas works, or how we've gotten this simple UI to work? Part of the assignment will be, and we'll take a look at that now actually. So assignment 9, we talked about this already, about the gaps in the floor, but this will be part of the maze generator, right? Because that's where we generate ultimately, or the maze instantiator, the actual part of the maze generator that creates the physical maze. But create gaps in the floor. And then when the player falls through, approximately 2 blocks below, which so you can check the transform is the Y positions less than a certain amount, right? Which should be less than 0. I think it's based on the top part of it. Then you should transition to a new screen that says Game Over. So create a new scene, very similar to the first scene that we looked at, which was just the title screen. And you can probably copy most of that. But that scene should say Game Over. And then pressing Enter there should load the title scene, right? And then lastly, add a text object to the play scene that just keeps track of how many levels you've navigated through. And you can probably do this with some kind of static variable. But any solution that accomplishes it is welcome. But altogether, all pretty easy pieces to put together. That was this week, which was Dreadhalls and our first foray into first-person games. Next week, we'll look at Portal. It won't look necessarily this good, but it'll look similar to this. This is a screenshot from Portal itself. But we'll look at how we can render to textures, how we can cast rays from our character, our first-person controller, how we can actually make it look as if we have a weapon or a gun or a portal gun, which is not too difficult. You just have to parent basically a model to your first-person controller. And then when we walk through a portal, how do we transition from from one portal to the other portal? So just teleport your transform to another position. But that was that. Next week is Portal, and I will see you all next time.